Imagine trying to keep a soap bubble intact in a windy room. Now imagine that bubble encodes the answer to a computation, and tiny gusts of air keep trying to pop it. Quantum error correction is the art of keeping that bubble alive long enough to do something useful. In plain English, quantum error correction is a way to detect and fix mistakes in a quantum computer without directly peeking at the quantum information. It's the protective layer that turns fragile hardware into reliable logic. Here's the twist compared to the familiar world of classical computing. In classical error correction, doubling or tripling the bits and voting on the answer works because bits can be copied and read at will. Quantum information doesn't allow that. Qubits can live in superpositions, blends of 0 and 1, and the no-cloning principle says an unknown quantum state can't be perfectly copied. On top of that, measurement collapses the state, like touching the bubble and popping it. So why care? Because without error correction, quantum computers drift off course after just a handful of operations. With it, algorithms for chemistry, materials, cryptography, and optimization shift from toy demonstrations to practical tools. It's the difference between a novelty and a new layer of computing. A picture helps. Think of the quantum state, the soap bubble, as being protected by a swarm of guard bees. Each bee is a physical qubit. The bees don't touch the bubble itself. Instead, they watch each other. If a gust of wind hits one bee, the others change their buzz in a way that reveals where the disturbance happened. The buzz pattern is the error signal. The bubble stays intact because the bees never poke it directly. So the simple version is this: spread one logical piece of quantum information across many physical qubits, listen for patterns that indicate mistakes, and gently nudge the right parts back in place, over and over, without collapsing the overall state. There's something quietly astonishing here. The system learns about errors while refusing to look at the data it protects. Slow this down for a moment. A few terms will come up. A physical qubit is the actual hardware element, a superconducting circuit, a trapped ion, a spin in silicon. A logical qubit is a protected virtual qubit built on top of many physical ones. The protection comes from redundancy and careful checking. With that mental picture in place, the mechanics can be explored without getting lost in symbols. Errors in a quantum processor tend to come in a few flavors. The most intuitive one is a bit flip error, a 0 turning into a 1 or vice versa. A less intuitive one is a phase flip. The rhythm of the superposition gets inverted, which can't be seen by just measuring 0 or 1 but matters deeply to interference. Real noise can mix both, and error correction needs to catch either type. Here's the thing. Since copying the qubit is off the table, protection comes from encoding the information across a group. Even a tiny example shows the idea. A basic scheme for guarding against bit flips takes one fragile qubit and entangles it with two others, distributing the information so that the whole trio collectively represents the original state. If one qubit flips, the pattern among the three changes in a recognizable way. What matters here is the kind of checking that's allowed. Instead of asking, "Are you a 0 or a 1?" which would pop the bubble, the system asks questions about relationships. Do these two qubits match? This is a parity check. It's another way of saying that stabilizer measurements look for consistency across small groups, not the values themselves. Those relationship checks are performed by helper qubits called ancillas. An ancilla briefly interacts with a few data qubits, picks up a yes or no answer about their agreement, and then gets measured. That measurement is safe to read because it tells nothing about the actual quantum data, only whether the group was consistent. The collection of these yes or no answers is called the syndrome. Think of it as the bee's buzz pattern. The syndrome doesn't say the logical state is 0.63 this and 0.77 that. It says something flipped near here. A classical decoder then interprets the syndrome and decides how to respond, often by applying the inverse of the suspected error to the right physical qubit. Put differently, the quantum part whispers where it hurts, and the classical part chooses the bandage. Take a short breath here. An important boundary has appeared. The computation is quantum, but the bookkeeping of errors is classical. Decoders run on conventional processors, CPUs, GPUs, FPGAs, and need to finish their work quickly enough to keep up. A small, concrete example helps fix the idea. Imagine 3 qubits storing a single logical state that has been spread into the joint pattern of 000 and 111. Suppose a stray noise pulse flips the first physical qubit. The group's relationship checks now disagree in a distinctive way. 2 pairwise checks report a mismatch, while a third still sees agreement. That specific mix, mismatch, mismatch, match, identifies the first qubit as the trouble spot. A targeted flip puts it back, and the combined state once again represents the original logical qubit. The key idea is that the repair never asked what the data was. It used consistency tests to point to the damage. Now broaden that idea, because real quantum processors need to catch both bit flips and phase flips, and they need to keep doing it as computations run. This is where a family of codes called stabilizer codes comes in, and one of them, the surface code, has become the workhorse for near-term hardware. It lays qubits out on a two-dimensional grid. Each qubit only talks to its neighbors. Local checks probe small tiles of the grid, producing a tapestry of syndromes that pinpoint where errors likely occurred. That local, two-dimensional design matters. Qubits on chips or in ion traps naturally interact with nearby neighbors. Local checks are less error-prone than long-distance ones, and they map cleanly to microfabricated layouts. As the grid grows, the code's distance grows, the minimum number of errors needed to fool the checker. Larger distance means stronger protection, though it costs more physical qubits. There's a deep promise at the heart of this approach called the Threshold Theorem. It says that if the underlying hardware errors are below a certain rate, adding more qubits and running longer sequences of checks can drive the logical error rate down exponentially. Above that threshold, throwing more qubits at the problem doesn't help. The bees get overwhelmed. For the surface code, the practical threshold is around 1% for basic operations. Modern hardware tends to target error rates well below that, 0.1% or better, to create margin. So a rhythm emerges. Encode the logical qubit across many physical ones. Run local stabilizer checks to gather a syndrome. Feed that into a decoder that estimates the smallest, most likely set of errors that could have caused those symptoms. Apply corrections. Repeat this cycle continuously while the computation proceeds. In other words, reliability arrives from a constant dance between quantum evolution and classical supervision. There's room here for an understated moment of appreciation. The computer is essentially steering through turbulence by reading ripples it intentionally creates. The act of gently probing the system to look for inconsistencies is what allows it to fly straight without looking out the window. Real systems anchor these ideas. Superconducting qubits on planar chips are arranged in square lattices that match the surface code's geometry. Microwave pulses perform the checks. Cryogenic controllers time the cycles. On the other side of the cryostat, fast classical electronics run decoders to keep pace, often targeting sub-microsecond turnaround, so corrections land before new errors accumulate. Trapped ions take a different route, moving ions and applying laser gates, but the logic of indirect checks and syndromes is the same. What about scale? The catch is overhead. One logical qubit, the protected abstraction, can demand hundreds to thousands of physical qubits, depending on how low the hardware errors are and how long the algorithm needs to run. With today's error rates around 0.1% to 1% for many operations, a practical surface code logical qubit often needs on the order of 1,000 to 10,000 physical qubits and an army of ancillas to monitor them. So the simple version is this: trading space for time. Spend many physical qubits and many cycles of checking to buy a long-lived logical qubit. That trade is expensive, but it's also the path to scaling. A few common points of confusion are worth clearing up. First, copying a qubit isn't an option. The no-cloning rule is a law of quantum mechanics, not a technical limitation. That's why these codes use entanglement and parity checks instead of duplicates and majority votes. Second, not every system with thousands of qubits is truly error-corrected. Many demonstrations today use error mitigation, statistical techniques that clean up results after the fact, rather than full-blown protection that runs during the computation. Third, raw qubit count doesn't guarantee progress. Error rates and the ability to keep a logical qubit alive for many cycles are the meaningful metrics. An example of a real milestone looks like this: a single logical qubit that survives thousands of error correction rounds with over 99.9% fidelity, or a small patch of a surface code demonstrating that adding qubits actually reduces the logical error rate as predicted. That kind of result says the threshold is being crossed in practice. Now back to the mechanics for one more layer of intuition. Bit flip and phase flip errors look different to the checks, so modern codes effectively run two intertwined sets of tests. One set watches whether pairs of neighbors match or not, catching flips of 0 to 1. The other set watches a different type of parity that's sensitive to phase. The ancillas that measure these parities are designed to interact in a way that imprints only the parity onto the ancilla. After interaction, the ancilla is measured and reset, ready for the next cycle. This choreography keeps the data qubits in superposition, untouched by direct measurement. Decoding the syndrome patterns is a computational problem in its own right. For the surface code, a popular method treats errors like paths on the grid and tries to pair up the syndrome blips with the shortest connections, a process akin to matching up footprints after a snowfall. Fast decoders map well to graphics processors or specialized hardware, and ongoing work aims to shrink latency to microseconds or less. Here's a quiet engineering marvel. The quantum chip, the cryoelectronics, and the room temperature decoders operate as one organism. Timing budgets can be brutal. If a correction lands late, it can make things worse. Achieving consistent, low-latency feedback is as critical as the qubit quality itself. So where does this leave the bigger picture? The practical stakes are substantial. Chemical simulation for drug discovery, designing better batteries, optimizing complex logistics. These are all problems where quantum algorithms promise leverage only if computations can run for long stretches without drifting off. Reliable logical qubits are the ticket to those longer stretches. There's also a realistic view of the road ahead. Building a quantum computer with many logical qubits means building a factory of checks, millions to billions of physical qubits, dense wiring, power-efficient control electronics, and fleets of decoders. It's a systems engineering effort at the scale of early supercomputers. It will not be quick, but the direction is clear. Some practical heuristics help when evaluating progress. Pay attention to error rates on basic operations, especially whether they're comfortably below the threshold for the chosen code. Notice whether experiments report logical error rates and how they change as the code size increases. Look for demonstrations where a logical qubit lives much longer than any single physical qubit would on its own. Those are signs of real error correction at work. There are trade-offs too. Larger code distance buys more protection but costs more area and control resources. Faster cycles catch errors sooner but demand quicker decoding and cleaner gates. Tuning these parameters is a balancing act, and different hardware platforms make different trades. Put differently, quantum error correction is a negotiation with noise. The system agrees to spend more qubits and more time watching itself, and in exchange, the environment's random nudges get averaged away. It's also worth noting what error correction doesn't fix. Correlated errors, where several qubits go wrong together, are harder to handle. Calibration drift, crosstalk, and integer overflow in the classical decoder can all leak into performance. Codes are robust to a point, but engineering discipline around the entire stack remains essential. One more explicit mental picture ties this together. Return to the bees and the bubble. Each bee's job is tiny and local. Compare notes with neighbors, report a buzz, rest, and do it again. No single bee understands the whole bubble, but the swarm's pattern, taken as a whole, carries enough information to keep the bubble intact. Errors are localized gusts. The swarm's choreography diffuses them before they chain into something bigger. If the wind picks up beyond a certain strength, the threshold, the swarm can't keep up and the bubble bursts. If the wind stays under control, adding more bees and tightening the rhythm makes the protection stronger. There's an elegance here that's easy to miss. The checks don't just detect problems, they define what it means to be correct. The allowed states are precisely those that make every stabilizer happy. That reframing turns error correction from patching holes into staying within a protected subspace. For those curious about numbers, a rough rule of thumb for the surface code is that the overhead, the number of physical qubits per logical one, shrinks quadratically as hardware error rates improve toward the threshold. Drop the physical error rate by a factor of 10 relative to the threshold, and the required code size drops by roughly a factor of 100 for the same logical reliability. That's why quiet improvements in fidelity matter so much. They ripple through the entire stack. Now pull this back to the real world again. Many labs have begun to show small logical qubits that outperform any individual physical qubit in the same device. Some can run hundreds or thousands of cycles while maintaining high fidelity. Others have demonstrated primitive logical gates perform directly on encoded data. Each of these results is a step from demonstration toward architecture. So how does this all answer the original question? How to detect and fix errors without destroying delicate quantum states? By never interrogating the data itself. By building a layer that only asks about agreement among neighbors. By leaning on classical computation to interpret those whispers quickly. And by repeating this process so routinely that errors are corrected before they pile up. What matters here is the mental model. One logical qubit is a bubble protected by a swarm. The swarm's job is local and constant. The buzz reveals where gusts hit. A fast brain outside the bubble interprets the buzz and sends tiny nudges back in. Keep the wind below a certain speed, and the bubble lasts as long as needed. Before closing, 2 moments of quiet wonder are worth mentioning. It's remarkable that entanglement, often portrayed as mysterious, becomes a very practical tool for maintenance. And it's equally striking that quantum and classical computing, seen as opposites, cooperate so closely here. Qubits carry the superposition, CPUs and FPGAs carry the vigilance. Expect the coming years to bring better materials, more uniform qubits, faster feedback loops, and decoders smart enough to learn patterns in the noise. Also expect honest reports of overheads. Building a fault-tolerant machine is not a straight line, but error correction is the compass. If this helped clarify how fragile qubits become reliable, a like and subscribe helps make more of these.